This is going to be purely Freecodecamp. We're going to speed run it again. We're going through, we did regex already. So we're going to go through the networking portion right now. So we have the networking portion, and then we have web services, Python objects, relational database stuff. So we have a lot to still go. Let's get right into it. So starting with networking with Python. Okay, let's get it.
Welcome to Networked Programs. This is chapter 12. Now we're going to learn a little bit about how we talk to resources on the network using Python. Now, this is a really quick introduction to how the network really works. I have a whole book that I wrote. It's also translated into Spanish on how the network works, starting at the very lowest layer, packets and everything, right on up. And it's actually really easy to read. I wrote it for a high school audience. It's a short book and pretty easy to read. If you read that book, you will understand that there is this layered architecture, the TCP architecture that sort of runs our network. At the lowest layer, that on one side here, this is your computer and this is a server computer. And if you sort of want a web page, it goes across the network, does this like 15 or 20 times, then it goes up into the server, reads the data, and then the data comes back, 15, 20 hops for the packets, and then it's shown to you as what you see. And so that's how it works. And there's these layers that we're not going to talk about in this section, but I talk about in that book. The layers of the link layer, which talk about how to get over one hop. The internet layer, which talks about how to construct, say, 15 or so hops to get packets back and forth.
Okay, so we're really just going over like normal networking stuff. So TCP, I learned this back when I was actually in school.
That's the sort of lower level bits. We're going to start at what we call the transport layer, and that's the layer where your computer sort of assumes that it can make a phone call to another computer, another process running on a program on this computer, talks to a program on this computer, and then it kind of comes back. Okay, and so we're gonna leave this alone. We're going to ignore it. We're going to assume that there's this nice reliable pipe that's going from point A to point B, and what are we going to do with the pipe? But if you're interested, take a look at the book. So we're just going to start with a pipe, some kind of a connection. We have two processes, process, and we have some kind of a connection between them. And it is a connection that we can both use to talk and to listen. In nerd terms, we call these things sockets, and that is one process running on one computer, another process running on one computer, another second computer connected through the internet somehow, and one computer speaks into that socket and it comes out, and the other computer returns something and it comes. And so this is a bidirectional protocol of data, which is a series of, in effect, data phone calls between applications. So the application might be, on your side, this might be your browser, Chrome, Firefox, Internet Explorer. On the other side, this is a web server. It might be Internet something from Microsoft, or Apache, or Java Tomcat. There's another program, and you are making phone calls between these programs. Now, in general, these servers here stay up all the time, and you sort of just can make a request when you feel like it in your program. But that's what we're going to do, and this is what we call a socket. So that little connection, that phone call, that data phone call, is what we call a socket. Now, you have to decide which of the systems you're going to talk to, and then which of the services on those systems, or which process. And so we have this concept called port numbers, and they're best thought of like extensions on phones. So one organization has one phone number, and it says, please enter the extension of the party you'd like to talk to. Well, that's kind of what ports are. They're like, here is, I'm a server, and I'm connected to the internet. Please enter the extension of the process that you would like to talk to. And so, for example, there might be processes running on various computers, and so the email is known to hang out on port 25 or extension 25. Login, insecure login lives on port 23. Insecure web lives on 80. Insecure web lives on 443. And there's a couple of different protocols. Say if you have your mail stored on Gmail, and you have a local mail client, say like Thunderbird or Apple Mail, that talks a protocol to pull that mail across, and those live on various ports. So these ports are those extensions, and by convention, we have standards that tell us what to roughly expect at those ports. So when you're talking to port 80, you expect to talk to a web server or an HTTP server. If you're talking on port 23, you expect to talk to a telnet server, and on. And so these are the extensions, the typical.
All I'm saying is, if it's not 443, you're doing some wrong. Just saying.
Commonly used default extensions for various network application processes that are serving us data. Now, sometimes you'll go to a URL and you'll see in that URL there's a colon and a number. That means it's a web server that's running on a port other than the official 80 or 443 port. Now, in Python, we can talk to these sockets, right? We can just talk to them, and it's really easy, surprisingly easy. We have to import socket because that's a library. It comes with Python until you can use it. You can't use it in your program until you say it. And then you basically in socket library call socket function.
That is the answer to our question here. So I'm pretty sure what Python library gives access to TCP sockets, which should be socket, but let's keep going.
Syntax is saying you're making a socket. Now the key to a socket, it's sort of like an unopened file handle. It's half of a file handle. It's an outward looking thing that's not yet connected. These parameters, you're just going to type them in. This says we're going to make a socket that goes across the internet, and it's a stream socket, which means that it's a series of characters that come one after another rather than a series of blocks of text. There's another kind that's harder to deal with, but we're going to do this. So this, don't worry about this line. Just know that this creates a socket, but does not associate it. The very next line, we get back a socket object in this variable that I'm storing in the variable mysock. And then when you want to make a connection across
socket.socket. What did he say?
These parameters, you're just going to type them in. This says we're going to make a socket that goes across the internet, and it's a stream socket, which means that it's a series of characters that come one after another rather than a series of blocks of text. There's another kind that's harder to deal with, but we're going to do this. So this, don't worry about this line. Just know that this creates a socket, but does not associate it. The very next line, we get back a socket object in this variable storing in the variable mysock. And then when you want to make a connection across the internet to the far end, you say, oh, hey, dear socket, extend yourself across the internet. Make the phone call to this host, data.pr4e.org, and on that port 80. So that's making the phone call. This is like the phone number, and this is like the phone extension. So that's, we haven't sent any data yet. We have simply rung the phone of a process, hopefully living on port 80. If it's there, great. This might blow up. This one here won't blow up, but this line here could blow up. If there's nothing sitting on that process, it would come back and say, oh, you tried to call, you got no answer. That's a legitimate thing to happen. Maybe you don't have a network connection, or maybe that service is down on that server, or the whole server's down. But so it's kind of amazing that we're sitting here in Python, and in 3 lines we have probably 500,000 engineers who built this thing called the internet, all these protocols and all this software, and we just made use of it in 3 lines of Python. And because this is one of the reasons that people absolutely love Python. So now that we have a socket, we have to ask ourselves, what kind of data are we going to send, and then what kind of data are we going to expect to receive across that socket?
I can tell that this section is going to be pretty interesting. I do like networking. Networking has always been fascinating to me, and to be able to work with it pretty easily in Python is going to be cool. So socket is the answer here. Perfect. We're 54% of the way there. We can do this in under 300 hours. I'm gonna have to do a tally of how many hours we've actually spent on this and like just see, but well, let's keep going. So we have internet standards. What type of HTTP request is usually used to access a website? That is the question. I believe I know what the answer is. I'm pretty sure I know what the answer is, but I'm curious to know what you guys think.
So now we have a socket. We are going to talk about what we're going to do with it, right? So the socket basically functions at this level. Your application is saying, make me a socket, which is sort of this endpoint. And then the connect actually connects to an application on the far side. And there's a port involved. So that might be port 80. And this is the far host, and that could be py4e.org or data.4e.org. Okay, and so the socket is solving this. And the question then, what are we going to send and what are we going to expect to get back? And that's what we call the application protocol. So we know that these two have made a phone call. It's no different than making the phone call and saying, you know, hello, right? And everyone knows that when the phone rings and you pick it up, you're supposed to say hello. And that's part of our protocol. So who talks first, right? So the dominant protocol that we use on this in this section is the HTTP protocol. The key is hypertext transfer protocol. It's dominant. It's really easy to use. That's why I use it as an example. But realize that there are many others like mail and file transfer and remote login and all kinds of other protocols. Each is a different application protocol. They all use sort of sockets at their lower level. But then on top of that, they layer the rules of the road for retrieving hypertext web pages. And we have used these for all kinds of other things. So the protocol, like I said, is like who answers the phone first? What do they say? What happens if the person doesn't answer right? Can you hear me now? Those kinds of things. And it's a real simple thing. And all you really need to do is so that both sides can agree, you have to write a thing that's like the rules in the middle and say, okay, everybody, as long as we all do this, we'll be fine. It's as simple as picking on which side of the road the cars can drive on. It works fine no matter which side, but if each car randomly picked, it would be really kind of a mess. So if you look at the typical URL, and this is one of the things that the web innovators in 1980 really invented that was wonderful, and it seems second nature today, but in 1990 it was rather revolutionary, in that these uniform resource locators included in themselves a protocol, the host to connect to, and the document to retrieve. So this is one of the clever ideas that the web came up with.
He forgot the L in HTML. Broken, call him out.
Because we used to have to pick a program like FTP or Telnet or whatever, SMTP, then we had to go to the right host, and then we had to talk to that host a certain way. So in HTTP, it's a really simple protocol invented in 1989 and 1990 by Timberly and Robert Caillou at CERN, and they created a protocol that we have grown to know and love and use for way more than retrieving documents, as we'll see in the upcoming chapters. So we're going to talk a little bit about what happens when you click on a page that has a link. Now, there's all kind of fancy stuff that can go on, but this is the basics. And so let's just imagine for the moment you start sitting looking at a web page, drchuck.com/page1, and inside that there is a hyperlink. It is a indication that says when you click on this page, go to a different page. And in that you see the name of the page that you're supposed to go to. So we click on this link, and that is a browser. This is an application. This is a process or an app that's running on your computer. This is the browser, okay? And when the browser sees the click inside your computer, then the browser makes a connection to port 80 on the web server, drchuck.com, and sends the request. This request that it sends is precisely specified by a standard, which we will see in a second. Then the web server does some magic work. Oops, let's go back. Then the web server does some magic work in here, reads some files, runs some code, does whatever, constructs an answer to our phone call, and sends it back. And it sends, in this case, back a web page in the format of HTML, the hypertext markup language, which is different than HTTP, which is the protocol that we're exchanging. HTML is the format of the document we're getting back. And in this has an anchor tag, href, end of anchor tag, and some highlighted text. And now your browser gets this back and then renders it according to the rules of HTML and CSS and JavaScript, etc., parses it, and then makes a pretty web page. And this web page happens to have a link back to the first page, and if you click there, it will do this over and over again. And that's the request-response cycle. And that's governed by a series of internet standards. These are standards that were built from the 60s, 70s, 80s, and 90s and continue to this day by a group called the Internet. It's not the right word there. It might have been revised. Oh, here's what a request looks like. This is how I'm going to get a document. That's right. We say get the document, followed by a space, encrypt your data back and forth. We don't use it anymore. But it basically is a program that can open a socket to a host.
Sharma.
I don't talk to programs. So remember to type this fast enough, and then you have to hit twice. So you have to have a blank line here. Just type this exactly as it's shown, and then you will get back the server if you do. And so if you do this, you can set this up in a way, nice usability. But the reality is, like in the Matrix Reloaded here, the kinds of things that really talented hackers are doing, use command lines and...
Okay, so one, I'm pretty sure we can all agree that get is the answer here. So let's keep moving.
In this section, we're going to write a web browser using Python. So we've already got a socket.
Before we do this does seem like an interesting video. What does the following code create? So we're going to look at this. For context, I've never really done this in Python, nor have I actually really done this in JavaScript. So this is new to me. So we're using the socket package that we covered in the last like 2 sections. So my sock equals socket.socket. We're going over the internet and streaming. So my socket.connect. So we have access to this. So we're connecting to this URL on port 80 or using protocol 80. No, maybe EMD or command equals get this URL. And then we encode that. And then we send the result of all this. And then while true, data equals receive 512. So a simple web server, a simple email client, a simple to-do list, a simple web browser. I'm pretty sure it's D. I'm pretty sure it's D. Pretty positive it's no. The question is, what does the following code create? So we have to look at this code block and really figure out what is it doing. But I don't think this is creating a web server because it looks like we're retrieving an actual page. So we're accessing. I think this is a web browser. But let's watch the video.
Okay, we know how to write a socket. In the previous scene, we played with a protocol and used Telnet to do it by hand. And now we're going to do it in Python. And what you're going to find is it's not that hard. So here we go. So the first 3 lines of this program, import socket, make the socket. Remember, the socket isn't really got the connection. So when you make the socket, again, we're going to make a stream-based socket, and it's suitable for going across the internet. The connection, it's like ring, phone call, connect to data.pr4e.org and port 80. And so that basically says extend the socket across and connect to a web server. And so there's got to be a piece of software running. And this will blow up if the software is not running, okay? So then, now we've got a phone. We've made a phone call. Now, whether or not the remote side says hello or not is up to the application protocol. And in this case, the web servers say nothing, and they wait for you to talk first. So we're the web browser in this case. And so we're going to talk first. And we know what, because we read the documentation, we know that we're going to send get blah, 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 space, blah, 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 ht1, and then 2 new lines. Return, return. Remember, we had to have a blank line. We'll talk a little bit about this encode. It's preparing the data to go across the internet. And then we say send it. And so this basically takes that little string and sends it across the network. And then this piece of software is waiting for it. And then the software goes and reads a file or does some other stuff. And then it starts sending us data back, which we can then choose to receive. So now I write a real simple loop. We're going to receive these things 512 characters at a time. So we're going to loop through, receiving 512 each time. And if we get 0 characters, that means its end of the stream is closed. And if you look at the little example from the previous one, you saw connection closed. When the connection is closed, we get an indication that it is because we ask for some data and we get 0 data. Otherwise, if there might be more data, this will wait. If the network is slow, you'll see, if you do a print statement in here, you will see that this will pause from time to time on a really slow network. If your network is fast, it'll just go blank and it'll be so fast it won't matter. But this is how we go. So this is basically until the entire socket, the socket is closed, we're going to read this data. And because this data is coming from the outside world, we have to decode it before we print it. And then when we're all done, we break out of here and we close the socket. So literally, that is an entire web browser written in 10 lines of Python.
Okay, so that confirms that it's a web browser. He's going HTTP header, cool stuff. Okay, so it's a web browser. Very good. That's actually pretty dope that you can make a web browser. These are all the basics of Python, really the basics of programming in general. And so right now we're going through networking. There's going to be web services, so like JSON stuff, XML, and then we go to objects and then relational database work, which would be very interesting. I actually haven't done that myself. That stuff I do need to catch up on, like Postgres stuff. So I need to get caught up on that. And then we're going through some projects, the scientific computing with Python project. So arithmetic formatter, time calculator, and so on and so forth. The goal of this is to try to do this under 300 hours. It's specifically listed as 300 hours. And so we're trying to do it underneath that.
Okay, so now it's time to teach you a bit of complexity about text processing. Until now, we've been ignoring the complexity of text processing. Everything that I have been doing, most of what I've been doing is in T, the Latin character set that the United States, Europe, lots of Western civilizations use this character set. And if you go back to the 1950s and 1960s, we were happy to have one computer and we didn't care what the character set was as long as what you typed on the keyboard came out on the printer. The internal representation didn't matter. And as the 70s and 80s came along, certainly 70s, we needed some interoperability, so they standardized on that character set. But they standardized on that character set, certainly in the West, that did not represent anything. And so if you look at this sheet, basically what it's telling you is for the various characters, there's some non-printing characters, white space, non-printing characters, and then here's some printing characters like the and key to 0, and then the uppercase characters, and then the lowercase characters. And there's 128 of these possible values. And there are nothing even for Spanish or French in here. And it's also why, by the way, uppercase letters in Latin sort lower than lowercase letters, and we saw that in some of the string stuff. And what these do is it maps and says, okay, and a lowercase a maps to the integer number 97, which in base 16 is 61, and in octal it's 141, but in binary it's 8-bit numbers. So these are 8 bits, otherwise known as a byte. And they're very efficient. You buy a disk drive, it's megabytes or gigabytes or whatever. That's how many of these kind of characters it can store. But unfortunately, this doesn't work for more complex characters. You can figure out these numbers inside of Python by using the ORD function. And so you say, what is the ORD, or the numeric representation of the uppercase H, lowercase e, and new line is a character as well. And so 10 is the position of new line. And this actually has to do with sorting, so that e, lowercase e, is higher than uppercase H. And that's just because in the simplest of sorts, we just sort them numerically. So new line, if you go back to the previous little sheet, new line is this 10 right here. It's that 10, which is a line feed, and that's a 10. And that's why when we print new line out, we get a 10. And so again, in the early days when strings were simple, we just represented them as 1 byte per character. But the problem is that as we have gotten more complex, and in today's modern world, it's simply unacceptable to say that the only thing computers can understand is ASCII. And so this leads to from the simplest of character sets to a super complex character set called Unicode, which basically is billions of characters, potential billions of characters for every language and every character set. And because there's so much space in Unicode, it's easy to take very small variations of characters and give them a space. It's so large that you can have pretty much any character that you want. So that's Unicode. The problem is that if we sent Unicode across the network, it would be way too large. It'd be this UTF-32, which instead of being
That's our answer.
8 bytes per character would be 4 bytes per character. And so it would take all of the data that we build and make it 4 times larger. And it'd be very difficult. And so what they've come up with is ways to compress this. And UTF-16 is this weird thing. UTF-32 is really the full Unicode pretty much. UTF-16 is a subset of Unicode. It's used in some countries. But the best practice for moving data across the internet or in a file that you're going to move between computers is what's called UTF-8. And so what happens is that UTF-32 is fixed length. ASCII is one byte. UTF-16 is 2 bytes. UTF-32 is 4 bytes. And UTF-8 has dynamic length, meaning that it is 1 to 4 bytes. And if it's only 1 byte long, it's perfectly compatible with ASCII, meaning that an ASCII file is also UTF-8. And so here's this little sheet. It's not critical that you understand this graph too much, but basically, as time passed, 2000 internet's coming out 2014, pretty much overwhelmingly the documents on the internet that you might retrieve are UTF. Now, so UTF-8 is a recommended practice, and it's sort of a compression. UTF-8 can represent all the things UTF-32 can represent. It's just a compression of it, so that and with an overlap of ASCII, which is awesome. It's what you want. I don't even talk anymore. So in Python, we have always had 2 ways of representing strings. In Python 2, the normal string was a byte string, was an ASCII string, was a Latin string, and if you wanted to represent Unicode, there was a separate kind of object that we had. And so 2 had bytes and strings that were the same. Sockets, a random world out there. We have to be a little more aware of the data we're dealing with.
All strings internally are Unicode. Working with string variables in Python programs, reading data from files usually just works. Okay, so we're just going to skip through this. UTF-8 was the answer. Cool. Using Url Lib and Python. Okay, so the prompt is, what will the output of the following code be like? Import lib.request. fhand equals urllib.request. You'll open this URL. For line in fhand, print line decode.strip. Okay, so we're reading from this text file that we're getting from this URL and looping through every line. I don't know what the strip part is though. So.
Okay, so now we're going to write a web browser again in Python, but it's going to even be shorter than what we did before. We did it in 10 lines using sockets. Now we're going to do it in 4 lines with URL lib. So URL lib really is just because the idea of opening a connection, sending a GET request, sending the new line, retrieving the stuff, breaking the headers out, doing all this stuff, that's so common, why not put it in a library to save ourselves some effort? So here's how we do it. We're going to read it in. We're going to import this library, so it's not part of, we had to import sockets before, but we're going to import URL lib now. And so this is really quite simple. It's like elegantly simple. You say URL lib, that's a library, this is part of a library module within the library, and this is a function. So let's call URL open, and then give it the URL. Now that's a string, which it's going to encode automatically for us. So it's taking care of all kind of pretty things for us. It does the get, it does the encode. Look back at that previous code. That's what URL lib is doing for us. Okay. Now what URL lib also does is it makes the connection, encodes the GET request, and then it actually retrieves, at this moment, it retrieves all the headers and keeps them for you for later. You can get the headers, but we're not going to see the headers. And it returns to you an object that looks pretty much like a file handle, because you can put this in for clause after the end. Now it's going to run that loop 1 time for every line of this file. And so the lines we're going to get back are bytes, and so we have to say decode. It doesn't do that for us automatically. We are going to have to decode them, and that's because we might need to decode them with a particular character set here. And then we're going to do our strip, and we're going to just print this out. So that's like open file, read through it, and print it. This is open URL, read through and print it. And that's as simple as it is. And so that's what happens. This is romeo.txt, and it prints out. Now the thing to notice is that there are no headers here. The headers have been consumed in the URL open. Again, there is a way to say, hey, give me
So it just prints the contents.
my headers, but for now, it's just going to eat the headers and keep them, and then you get to read all the data, and the loop runs, and this loop runs 4 times, and out come the 4 lines. You can go ahead and run this one. It's super easy, literally super easy. You can do anything you want. Treat it like a file. You just have to remember to do the decode bit when you treat it like a file. And so that code import it, we're going to open it, we're going to make a dictionary, we're going to loop through, we're going to split it, we have to add the decode just to make sure, because that line is bytes, not string, and then we're going to go our words, we're going to go through the line, and then each line we're going to bounce through the words, the inner for loop is bouncing through the words, and then we're going to the next line, and then we make ourselves, and this is a dictionary, and we print that dictionary out. Now this, in effect, other than importing this, opening it differently, and doing the decode, this is exactly how we would process a file. And so by using URL lib, you really reduce the complexity of retrieving and reading network resources to the same complexity of reading and dealing with a file locally on your hard drive, which is pretty. One of the things then we can do is read web pages. That was a text file, but you can get HTML. And so here's how you read a web page. And it's the same kind of code. We open a URL. This one happens to have HTML in it, and we read through it, and out comes the HTML. Remember that the headers are there, but they've been eaten by URL open for us. And now we could write a browser that would parse these less thans and greater thans and make links, et cetera, et cetera, et cetera. So if you can come up with ways to find these links, you could actually write a bit of code that would then have a loop that would.
Okay, so we're just going to skip through this. It's going to print the contents. Okay.
So now we're going to.
Okay, So this portion of the course might be interesting for a lot of us. Web scraping. What Python library is used for parsing HTML documents and extracting data from HTML documents? So we have socket, HTTP, beautiful soup. That sounds familiar. Pretty biscuit, wonderful salad, AP parser, and Grunkle-stan. That's a great name, by the way. Grunkle-stan.
Talk about what you would do with a web page once you've retrieved it in a Python program. Call this web scraping. And so web scraping or web spidering is the act of retrieving a web page, extracting the links from those web pages, making a queue of unretrieved links, and then moving on. And eventually the idea is if you had enough time, energy, bandwidth, and storage, you could find your way to most of the web pages on the internet that are point to or are pointed to by other web pages. And so you might have all kinds of reasons to scrape data. You might have a blog that you posted. You might have, who knows, maybe you put some data in a system. Maybe the system's being shut down because it's being retired. You can do all kinds of things. You could write a little thing. I was talking to somebody who wrote a thing to retrieve something and check and then send a text when something changed. All kinds of stuff. Or you might make yourself a search engine. But be careful. Not all websites are happy about you using a robot to retrieve their content. Some of the websites, as we'll see, demand that you log in and they track what you do. And if they think you're doing something bad, they will shut your account off. Other websites will track what you're doing without you logging in, but then shut your address off. And so you have to be careful. You should read up. You should figure out what sites allow you to scrape them. Now I have some sites that I've set up that you can play with to make it so that it's legit. So parsing HTML is difficult. Some of the simple examples, you could probably write a regular expression or certainly some splitting and some whatever. And what you would find is you would write that code and you'd retrieve your first 5 web pages and it would seem to work. And then it would encounter some really weird but legitimate HTML or maybe even slightly broken HTML. So the web is full of broken HTML and your browsers just look at it and go like, oh wow, more broken HTML. But they don't put up error messages and so people just leave broken pages up. But your Python program is going to see those broken pages. So what you would do is you're like, oh, here's a new weird way to do an anchor tag. I'll change my code. Oh, and then run for another 100 pages. And like, oh no, here's a new weird way to do an anchor tag. And the problem is that you're going to find a lot of different ways to mess up an anchor tag. And someone's already done it. There's a software called Beautiful Soup, and we have installation instructions on how to use it. And really what it is, it's somebody just spent months figuring out all the nasty things that could happen and compensated for it and gave you a nice wrapped interface that just says, look, you give me the HTML and I'll give you back the tags. Okay? And so it's called Beautiful Soup. And so you have to install this. There's a couple of ways that you can install this. If you're good at extending your Python, you can just extend and install Beautiful Soup for all Python programs. If you can't change your computer's configuration because you're on a school computer or you're using a USB stick or something, then there's a way to download this file that I created called bs4.zip. And so what you do is you end up with your file called url links.py and then a little folder called bs4, which is a folder that has a bunch of files in it from the zip file. And then you can run it. And so it'll pull it in and you'll import from bs4 Beautiful Soup. And then it's either going to pull it in from the folder you do, or if you've installed it using the Python installer, it will also just, you don't have to put this file in. So it's up to you. You can either do it one of two ways. So this is a little bit of code. Now Beautiful Soup is a complex library. And so just because this looks easy, doing things in Beautiful Soup, you might have to actually read a bit more to figure it out. But we're going to just read this. We're going to import Beautiful Soup. We're going to ask for URL right here. We're going to take that URL. We're going to open it. URL open. They give URL and read the whole thing. That means we're not writing a loop. We've read the whole thing. That's okay as long as you know that the file's not so large. And then we're going to pass the data we got back. And this is going to be bytes, but Beautiful Soup knows all about bytes and all about UTF-8 and it figures that out. And you just say, hey, take that stuff I just got and tear it apart using HTML and give me back an object, a soup object. Now the soup object is something that you can run queries against. So it parses it. It deals with all the imperfections and inconsistencies in this HTML byte array. And it fixes that. It gives that back. And so there's various things you can do. And you got to go look at the Beautiful Soup documentation. It could be a whole class on Beautiful Soup. So here's the thing you can do is this object, you can call it like a function and say, hey, give me back the anchor tags. And anchor tags, of course, are the tags that say href equals blah, blah, blah /a. So all of this is an anchor tag. And then we're going to loop through the tags because there could be more than one of those anchor tags in the file. And then we're going to pull out that href. And that's what this does. We're going to loop through all the tags and print out the href. So if you tell it to go to drchuck.com, it will show you the one external link in drchuck.com. And so I've got an assignment that sort of goes into that in some more detail. But this chapter has been a whole bunch of interesting stuff. We started with a TCP IP model and talked about sockets that are phone calls between computers, and then how applications protocols are developed to say what we say on those phone calls. And we've explored then the HTTP protocol, which is probably the most likely thing you're going to see. And then we played with all this in Python and saw that Python is really good at this. You can.
Okay, so he's just giving me a summary. Beautiful Soup is the library. I'm actually curious now. I'm going to save this for later. Man, look at this documentation. This seems so old school, no? Okay, gotcha. Okay. All right, web services. So we've just now completed all of the networking portions of this course, and now we're going into web services. I guess you could see this as still part of the networking side, but let's get into it.
Hello and welcome to Chapter 13, Web Services. So what we've been doing so far is we've been using the request response cycle. We've learned about sockets, we've learned about Url Lib, and we've actually learned how to pull HTML and even flat text off the internet. But what we're going to talk about now is using that same request response cycle to retrieve information that is specifically designed for programmatic consumption. So that we had to have this Beautiful Soup, which sort of did a hack job or solve the hard problem of parsing HTML. But why not produce data in a format that makes good sense to a program? Because programs want to talk to each other. If you recall, the whole idea of a socket is to have one application process sending data to another application process. And so if we think about this for a moment and we realize that we have all these programs, they can be written in different programming languages and they're all connected. And so they might want to send data back and forth through the network. HP programs, JavaScript programs, Java programs. And so we have to decide on a protocol that is independent of any programming language. And we call that the wire protocol, because if you were to take some connection and watch the exact characters that go back and forth, that's what you would see if you were monitoring the wire. So that's why we call that the wire protocol. And so the idea is that we have to agree on a format that is going to represent the data, and you can't make it a Python-specific format or a Java format. And when we take the data from the internal representation, maybe a Python dictionary, to send it to the wire, we call that act serialization, and that's going from internal representation to the serial representation or the wire representation. And then here's an example of a person with a name and phone number with using less than and greater than. This is an XML example. And then in the far end, in a different programming language, it receives this and then deserializes and then turns it into some useful structure inside that programming language. And so this is an example of a wire protocol that's using XML, and that's one of the formats we're going to talk about. Another format that we're going to talk about is a format called JSON, JavaScript Object Notation, and it is simpler and easier, but it's not as precise and descriptive as XML is. And so while you'll find that most of the things you run into, especially if you're talking to APIs of one form or another, you'll find that JSON is very common. XML still holds sway in places like documents. So if you look at docx at the end of a Microsoft Word document,
I don't know if I pulled the actual answer out of this, but I'd imagine JSON is the easiest way to send data. And what do we think, chat? Data and JSON and do you think that's the answer here? Or JSON and text? So I was right. Okay, let's test it. Nice, 64% late. Let's get it, dude. On to XML.
So one of the two ways that we mark up data is XML. The other JSON. First, we'll talk about XML. We'll talk about XML more for a longer time when we talk about JSON.
Okay, what is wrong with the following XML? To be honest, I haven't really worked much with XML. I'd imagine it's this right here, lines 3 and 4. That looks off to me. There's no closing tag on the phone. Yeah, I'm just off of things that I know. This would probably be the problem. Lines 3 and 4.
XML stands for Extensible Markup Language. There was a number of markup languages in the 90s that were out there, ways to send data between computers, and none of them was like amazingly better than the other. But in the early 1990s, as HTML came out, the idea that we could use less thans and greater thans, or angle brackets, some people call them. Once HTML made angle brackets popular as a representation format, it was pretty natural that we would find a data representation format that would take a similar approach. And so inside XML, we're going to talk about tags, we're going to talk about attributes, we're going to talk about data, and we've already talked about serialization and deserialization. Serialization is the act of taking data inside of a computer in one programming language, setting it up for transport, transporting it across, and then taking it back apart and turning it back into the data in whatever internal data it needs to be in the destination system. So here's some basic XML, so we can take a look at the various things that make up the XML.
This just looks just like HTML. Okay, can we just keep going through this? So this is, I'm pretty sure it's because of the phone tag. Yeah, XML schema. Oh,
now we're going to talk a little bit about XML schema. XML schema is a language that allows you to decide on whether or not a particular XML document meets a contract and arrangement. So you have two pieces of software exchanging data using XML. And what if one of them, if they're all working, nobody really worries too much about it. But if all of a sudden one breaks, you change one side and the other one breaks, whose fault was it? Was it the side that got changed or the other side? And so you could argue. So what you'd like to do is before you set up these arrangements between these applications, set up a contract. In a way, they're kind of like the RFCs are, except that their scope is between pairs of applications. And so it itself is XML. And it basically, what we do is we take an XML document, XML schema contract, and then we either say that's good or that is bad. And that's called validation. A piece of software that validates XML when given a schema is called a validator. And so an XML document, here we have our little XML document, we're passing it to the validator. And then we have a schema contract, which is itself XML. It's a particular kind of XML, that XS colon complex type. That's just a tag. Colon is a legitimate character for the name of a tag. Name equals person, that's just an attribute. And so XML schema is a particular format of XML that renders an opinion about what XML is supposed to look like. So there's a number of different XML schema languages. The one we're going to look at is one that came a little bit later, that's very common, called XSD, which is the World Wide Web Consortium's schema specification.
Got my answer.
Often you'll find files that have suffixes of .xsd that actually contain the XML, just like we're going to show you. So if you recall, there are simple elements which have text children, and then there are complex elements where other nodes are children of other nodes. And so we can say this. And so here we have a little bit of XML and the XML schema that makes sense with that. So what we're saying is the outer tag of this legitimate XML is supposed to be a complex tag with a name of person. And so there we go. That looks good. Good. But then there is a sequence, and then there is a simple element, a name of last name, looks good. And it's a string, that looks good. Another tag that's a named age, that's of type integer, that's good. And then a thing that's called date born, and then there it looks like a date. So we check all these things, and we can basically say, yep, that is a good XML document according to this schema. And you don't have to write this generally, but there is software that reads these two things and comes back with a true or a false, and now you even have some detail as to what went wrong with this particular schema. Here's some more that you can do with a schema.
So we're just going to skip through it then. Not a big deal. We'll keep moving forward. Okay, so the JSON part. This is the bread and butter that we deal with on a day-to-day basis. What will the following code print? So we have JSON. Okay, so this is what is this triple quotes? This looks like a comment. So is this not even valid here? I'm gonna go on a whim and say error. I don't think this prints anything because all of this array of objects is commented out. Because the triple quotes is a comment or a multi-line comment in Python. Triple quote is like backticks in JS? I don't think so. Info equals JSON.loads data print info one name. I honestly don't think this is gonna print anything. In theory, if we were actually gonna print name at index of 1, it would be this. It allows for a multi-line string, but this is JSON. So am I wrong in saying that this is gonna print an error? Would it actually print this? Chat, I'm sticking to error. I'm sticking to error. I don't think that's correct.
So now we're going to talk about the other serialization format, JavaScript Object Notation. Chances are good, as you go out there, you will very likely encounter more JSON than you will XML.
Who's this? Oh, Douglas Crockford. Gotcha. Okay, so he's the reason why we do JSON.
Not that XML is bad. XML is better for rich and hierarchical documents, whereas JSON is best for just pulling data out of a system and moving it between two systems with a minimum of fuss. This is Douglas Crockford. I have a great interview from him. He's a funny guy, very smart. He claims he didn't invent JSON, he discovered it because it really is based on the literal notation for JavaScript. And it actually looks a lot like the Python literal notation for objects and for lists. Now, Douglas Crockford has quite a sense of humor. He wrote this book called JavaScript, The Good Parts. That's the little one right there. And then JavaScript, The Comprehensive Guide. And the sense of humor is all the stuff that's in JavaScript that's not too useful. And while this is sort of a tongue-in-cheek, it also is trying to say that JavaScript, what Crockford is really saying here is JavaScript is a great language as long as you avoid the tricky bits and keep it very simple. And JavaScript is indeed a great language. But JSON comes from JavaScript. You can read about JSON at json.org. JSON is not an international standard. It's not like an RFC. It really is. Douglas Crockford decided to register json.org and typed in some pages, and people started reading it, and people started using it. And partly that was because it was truly derived from the JavaScript literal syntax. So we're all ready to code. Here is some Python that's going to process some JSON. Keep it straight. Python, process JSON. So again, I'm using the triple quoted string here. Now you'll notice the syntax that we were using is not angle brackets, but instead curly braces. And so the curly brace, and then within the curly brace, you have key value pairs, name, colon, chuck, and key, colon, value.
If this works, if this actually allows JSON to load.
Both sides have quotes. You can also have objects within objects, curly brace, key value pairs, key value, key value. Looks a lot like Python. And then you can do this. And so this is a structure that has one key value pair that's a string, another key value pair that's an object, another key value pair that's an object, and then these are key values within those contained objects. So this is a string that, again, probably was retrieved across the network from some other place. And we're going to pass that string into the JSON library. Load S stands for load from string. So it reads this, parses it, looks at all the white space. Again, doesn't matter too much here unless it's in between double quotes. The white space doesn't matter. And so it parses it and then returns us a dictionary. So the thing that's different about JSON is that its structure and representation are simpler than XML. So in Python, everything either comes back as a dictionary or a list, or a dictionary within a dictionary or a list within a dictionary, but it's all dictionaries. It's not a separate structure that you have to do gets and finds and find alls and lookups. So it's right there. So when we get this back, because this is a curly brace, info is a dictionary. And so we can just use the standard syntax of Python, info subname. Let's clear this. So info subname, we'll go find Chuck. So if you compare that with the XML, that's just a lot easier. Now, when we have info sub email, that's this thing. So info sub email is that thing. And then sub hi is this. So that's what comes out here. Okay, so it's really nested dictionaries and lists. We haven't seen a list yet, but this is a set of nested dictionaries that it parses. And it's equally simple in other programming languages. This is a little more complex version where the outer element is a square bracket, which means it's going to be a list. And so we have a list of 1, 2 things. So this is a list of 2 dictionaries. So there's 2 dictionaries inside that list. So again, we take this string and we load it into, use the JSON parser to read the string and give us back, in this case, info is a list. It's got 2 items. If we print out info, it'll give us 2. And we're going to iterate through. And so if we're going to iterate through, item is going to first be this, and then it's going to iterate to this. And it's going to print out item sub name, which is going to print out Chuck, item sub ID, which is going to print out 001. Now you'll notice that there is no attributes, and that's because JSON is simpler, but we can have the X, and it just is another item, so we say item sub X, and that's going to print the 2 out. And then it'll iterate to the next one, and it'll print out the same thing for those guys. And so JSON is simpler because you can't represent as complex a data structure, or you have to compromise and map it into a simpler data structure, but then it is lists and dictionaries, and so once you've got it parsed, it is easier to understand to make use of. So that was quick.
So we were wrong. Let me try this, okay? Because I genuinely thought that this was going to be an error. If in actuality, it would probably be this. Since we're digging into info, we're going through, go through the list, and we're going to this dictionary since it's index 1, and then that dictionary's name value. But let me check to see if error is the right. It's not an error. I need an explanation. Wow, interesting. It wasn't an error. Huh, that's new to me. I've never seen that, but all right.
So the service-oriented approach is a way we approach solving a complex application problem where all the data really isn't present in one computer system. It's somehow spread out over the internet, connected by the internet or internal network. And so the idea...
With a services-oriented approach to developing web apps, where is the data located? Spread across many computer systems connected via the internet or internal network within different services on the main web server on a separate database server.
Is that some applications just can't contain everything. The perfect example is a travel website that can book you a flight, book you a car, buy tickets, book you a hotel, and do all these things. Well, that travel website is neither a hotel nor a rental car company nor an airline. But what it really does is it talks to all these services somewhere else on the web on your behalf, and it makes reservations for you. And so you have this convenient user interface that says, oh, here's your whole vacation. I'm going to figure all this stuff out. And then you say go, and goes book, and books on all these other systems. Now it requires a lot of infrastructure, a lot of coordination, and a lot of effort to make sure that your application can talk, and these other services that are out there in the internet have good contracts, and you know exactly how to send data to them and get data back from them. And so initially, when you're building a service-oriented architecture, often you have one application, and it's all internal. Often it's all one language. And then maybe you'll say, oh, wait a sec, we want to take part of what we do and put it in a second system, and then come up with a set of rules between the systems, and then more and more. And this is a video that talks a little bit about the process and complexity about taking these interfaces between applications and applying standards to those interfaces.
Oh, that was it? Okay. It's not that one. Oh, wow. I got them all wrong. It's A. All right. So the answer was spread across many computer systems connected via the internet or internal network. Good. Keep rolling. Okay, so we're on APIs. Let's see where we are. We have 2 more sections on web services, and then we're out of this section, and then we move straight into objects.
So now that we're solving our problem using a series of cooperating applications communicating across a network, we're going to talk a little bit more detail about the notion of what we call web services. And in this, we're going to take a different perspective. Instead of building our application and breaking it into pieces, we're going to have an application that's going to really consume an API from somebody else. So there is some other provider of this API that's not us. And so that if you're going to talk to somebody's data like Google or Amazon or Twitter, they're going to say you have to use our API. So what's that? So an API is a contract that says, look, if you do this and this and this, we're going to give you data this way. And they set the rules. They tell you what the URLs are. They'll tell you if it's XML or JSON. And this is called the application program interface. And it's something you read and you understand. And so you go look at the documentation. This is documentation for the Google Maps API. So it turns out that Google knows a lot about maps. It knows a lot of data. It knows how to search maps. And it actually provides some of those features to you that your application can take advantage of. I took advantage of this at one point by asking all the students in one section of one of my online courses where they were, and I just let them type in where it was. And then I said, well, I don't know how to code any of that. So I used this API doing what's called geocoding to look all those places up and get precise latitudes and longitudes for the ones Google could figure out. And that saved me a lot of work. Now, these are expensive resources, but I could be patient and make use of these resources, which as long as you use them not too much, they can be free. We'll talk a little bit more about rate limiting and what's free and what's not in a bit. But you start by reading documentation. It says, do this, hit this URL, hit that URL. So if you read that documentation, you will find that there is a URL that you can hit. And they tell you where to go. And then you go to this URL, you add a question mark, and then you say address equals, and then Ann Arbor plus, and there's all these rules. These are called URL encoding rules when you have key values on URLs. The plus means space and %2c means comma. So these are called URL encoded. Don't worry too much about that because we're going to have a magic library like we always do in Python that takes care of this. And so if you were to hit this URL, you type it in the exact right way in your browser, you will get back a JSON document. It's an object that has key value pairs. The first value is the status, then it has these results, and it's a list, and you dive down, and eventually you can kind of find the latitude and longitude of the thing that you are looking for. And so the idea is, can we write a program that can read this? And so here's our little program that reads this. And a lot of this is comfortable. You've already seen some of this. You import URL lib, we have to parse them JSON, we grab the URL, and then we're going to write a little while that's going to ask for a location, and we can type that location in, and we've got to concatenate with this URL the location equals, and there is a bit of code, a library called Parsing Html that takes the key and the value, so the address equals, and then whatever this text is that we read in from the user, that goes in here, and it does that URL encoding with the pluses and the %2c, and all that stuff is taken care of, and that is our URL that we're going to pass to URL open. So we print out that we're going to retrieve it, prints this out, and if you look at this, it's too long, it has all that fancy stuff on it, and then we read it, we open it with URL open, and then we read it and decode it. So these two things, hit this URL, decode it, and then we retrieved 1669 characters, because it's just in this case, because we decoded it, data is a string now, that's read is bytes and data is a string. So we read that many characters, 1669 characters, and then we're going to take this data and we're going to parse it with JSON, and we might get bad data here. It might blow up, but it might work. And so in this case, it works. We have an error that basically says if we got a bad thing, we're going to blow up, but in this case, it doesn't blow up. And so now we're going to dig through. And if you go back, let me just go back. So the results, sub-zero geometry. Let's show you how that works. So results is the first key. So this is a dictionary with a key of results, but then it has a list. And the 0 item, this list starts here and goes there. And I'm only going to show part of it, but there's many things here. So the 0 item this is the sub-zero. And then geometry within that sub-zero item. So if we look at that, it is the outer dictionary, the first item of the list, sub-geometry. So that grabs one part. That grabs this part.
Pretty sure we all know how to work on APIs and stuff. Program interface. That is what API stands for. Okay, last section on the web services. So we go through API, rate limiting, and
now we're going to talk.
Oh, before we start, when making a request from the Twitter API, what information must always be sent with the request? Probably a search term, but if it's required, you could see both, but I would say a key. No, maybe. Chat, it's either between search term or key. Key makes the most sense. It's just search term also does make a little bit of sense. Key, final and lock it in. Let's go.
Talk about API rate limiting and security. The key thing is that the Google API and the Google data is super valuable. And you could build a website that did nothing but ask the person for something and then showed them that place and make it be a map searcher. And you added so little value and Google did all the hard work. And so they protect these somewhat. Sometimes they'll say you can only do 50 of these a day or 500 a day or whatever. That's called rate limiting. And sometimes they say you've got to log in, you've got to create an account and get a key with us and then present your key. So that means that your account only gets so many.
We're like 36 seconds in and we already got the answer.
And they keep track of who's using their service and how much they're using it. Google gives you even a dashboard that tells you some of this stuff. It's nice. The other thing, sometimes an API is free and then it becomes popular and they decide they're going to put a key on it or a rate limit on it. So you got to play this game with them and the rules kind of change as things progress. So that geocoding API that we're talking about has at one point in time 2,500 requests a day. You can get more requests if you get it. Now, another API that we can talk about is the Twitter API. Now, Twitter API started out as a free public API, but then Twitter realized that people were making more money off of Twitter's data than Twitter was making off of Twitter's data. And so Twitter makes it so that you have to have an account. You can only request data from their API is if you use your account key to sign that. And so there's a whole series of getting and issuing keys and then using those keys. And I'll just give you a short summary of the kind of code.
Okay, so API rate limiting and stuff like that, that's pretty... Oh, TW URL is an actual library that we can put Twitter URL. So the URL, screen name, count 5. It's pretty standard stuff. Okay, so the key. Very good, chat. 75% done with the course. 75. This is probably where we're going to stop at the course, but I'm still going to be sticking around for a little bit. But this is... We're going to go on to the next sections the next time we do this, which is going to be objects and then relational database stuff. And then at the end, we have some data visualization. So good. We're almost done. I'm pretty sure we're knocking this out under 300 hours. So just saying.